Ever wonder how doctors choose the best treatment for a patient when there's no clear answer? What if I told you that quantum physics, the same science that powers quantum computers, is now helping solve one of medicine's trickiest puzzles? Let's break down a groundbreaking study that's using quantum computing to make medical research fairer, faster, and more accurate. Imagine you're a doctor trying to decide between two surgeries for colorectal cancer, a traditional open procedure or a minimally invasive laparoscopic one. You want to know which is better for survival. But here's the problem: patients don't randomly choose their surgery. Factors like age, tumor stage, or even a surgeon's preference can skew the data. This is called selection bias, and it's a huge hurdle in medical research. To fix this, scientists use something called propensity scores, a way to mathematically balance patient groups so comparisons are fair. Think of it like matching people with similar traits, so you're really comparing apples to apples. But traditional methods, they struggle with complex, high-dimensional data. That's where quantum neural networks, QNNs, come in. These aren't your average computer models. QNNs use the weird, wonderful rules of quantum physics, like superposition and entanglement, to process information in ways classical computers can't. In this study, researchers trained a QNN on data from 1,177 patients, including details like age, BMI, and tumor characteristics. They focused on 4 key factors and tested their model under different conditions: perfect quantum hardware, simulated noise, and real-world imperfections. The results? In small datasets, like a sample of just 100 patients, the QNN outperformed traditional methods like logistic regression and gradient boosting. Even with noisy quantum hardware, the model stayed stable, thanks to special techniques that account for measurement errors. When they used these QNN-based scores to balance patient groups, the differences in key traits, like age or tumor stage, dropped to less than 10%, a sign of a fair comparison. But here's the kicker: after adjusting for bias, there was no significant difference in survival rates between the two surgeries. That suggests earlier studies might have been skewed by how patients were selected. Now, this isn't about saying one surgery is better than the other. It's about showing how quantum computing can make medical research more accurate, especially when data is limited or messy. With QNNs, scientists might uncover truths that classical methods miss, like hidden patterns in patient outcomes or subtle treatment effects. But let's zoom out. How do we even begin to compare treatments when real-world data is so messy? Let's take a step back and look at a 2016 study on colorectal surgery that used traditional statistical tools to tackle this very problem. This study compared 2 approaches: laparoscopic minimally invasive surgery and traditional open surgery. Laparoscopic techniques use small incisions and a camera to guide tools, offering faster recovery but raising questions about long-term outcomes. To analyze the data, researchers used the Cox proportional hazards model, which tracks how long patients remain complication-free. They also relied on the Kaplan-Meier estimator, a visual tool that maps survival or recovery rates over time. But here's the challenge: real-world data isn't clean. Patients vary in age, health, and tumor stage. To create fair comparisons, scientists used propensity score matching, a method that pairs patients with similar traits like age or tumor stage to isolate the treatment's true effect. They also applied matching weights, which adjust the influence of certain patients in the analysis to balance differences. The 2016 study found that laparoscopic surgery had a survival advantage, but this new quantum approach revealed something different. When researchers adjusted for hidden biases using QNNs, that advantage vanished. This suggests earlier studies might have overestimated laparoscopic benefits due to unbalanced patient groups. So what does this mean for medicine? It means we need to rethink how we analyze data. Traditional methods are powerful, but they have limits. Quantum computing isn't a magic bullet. It's a tool that can handle complexity in ways we've never seen before. Together, these approaches could help us uncover truths that were previously hidden in the noise. The future of medical research isn't just about better algorithms. It's about asking smarter questions, using tools that can handle the messiness of real-world data, and ensuring no patient's outcome is lost in the numbers. Whether it's quantum computing or traditional statistics, the goal remains the same: to save lives through clearer, fairer science. Thanks for watching. If you want to dive deeper into how data shapes medicine, hit subscribe. And let me know in the comments, what medical mystery would you like us to solve next? Stay curious and keep questioning the numbers behind the headlines.